Automatic Adaption of the Step Size in Gradient Descent Training, by Albino Nogueiras Rodriguez and Ignacy Nogueiras Marco, from somewhere near Barcelona, Spain. This paper addresses the problem of selecting an appropriate learning rate in gradient-based optimization algorithms. In our approach, the algorithm automatically generates a sequence of learning rates that converge to similar values, independent of the initial one. Our method does not use any really innovative techniques, just well-known strategies combined with a bit of care. Besides the standard SGD, the proposed algorithm is also compatible with other approaches, such as ADAM and ASAM. The idea behind gradient descent-based algorithms is that the gradient points in the direction of maximum increase of the function. Hence, given a smooth function of the system parameters, its probably local minimum can be reached by iteratively applying a small variation in a suitable direction. The direction of variation may be the gradient of the function, but more often it is something closely related. For example, the gradient multiplied by some kind of approximation to the inverse of the Hessian, as in ADAM and other Newton or quasi-Newton methods, or an exponentially weighted average of previous gradients, as in stochastic gradient search with momentum, commonly known as SGD. The problem is, what is a small enough variation? The variation is determined by the learning rate mu, so a careful choice of learning rate is needed to ensure proper convergence to a minimum. If we use a learning rate that is too low, the algorithm will take many steps to approach the minimum of the function. The algorithm will certainly reach the minimum, but perhaps at a rate that is too slow to be practical. Conversely, if we use a learning rate that is too high, the algorithm will oscillate around the minimum, increasing the value of the function at each step and eventually diverging. What's more, if the function contains instabilities, there will be a high probability of reaching them, which will have disastrous and irreversible consequences in the system. Thus, choosing an appropriate learning rate that leads to the vicinity of the minimum in a reasonable amount of time is a critical need in function optimization using gradient methods. Looking for a solution to the problem of learning rate selection, the authors conceived ACME, the Galician acronym for quadratic adaption with exponential memory. Our main assumption is that the appropriate values of the learning rate don't change too much or too fast during the training process. If it's good now, it won't be too bad later. The basis of the algorithm is steepest descent, which avoids the need to choose the learning rate at the cost of performing a line search. In our case, we perform this line search using a quadratic approximation of the loss function. However, it won't always be possible or convenient to use this approximation. Each case must be considered depending on the values of the function and its derivatives. The optimal learning rate is then used both to adjust the system parameters and to choose the tentative learning rate for the next iteration using an exponentially weighted moving average. We use a look before you leap strategy because instabilities are usually close to the optimal values of the learning rate, so the learning rate used at each step is always an interpolated one, avoiding extrapolations that could inadvertently lead to instability. Steepest descent consists of using the Cauchy learning rate at each iteration, that is, the one that leads to a local minimum of the loss function. The main advantage is that it provides a good choice of the learning rate. However, it doesn't guarantee maximum convergence speed, although it usually converges fast enough to values of the loss function close to the minimum. Also, using steepest descent requires determining the optimal learning rate at each iteration, which is usually done by performing a line search. This means that we need at least two evaluations of the loss function and its derivatives. The geometry of the loss function is sketched at each iteration. At iteration I, the loss function is defined as a function of the learning rate, mu. The value of the loss function is calculated along with its derivatives, both at the initial state of the system and after applying the tentative learning rate. The actual learning rate used in this iteration is estimated from these values. To avoid instability, this value is limited to the range between mu equal to 0 and mu equal to the tentative rate. Knowing the value of the loss function at 2 points and its slope at least one of them, we can fit a parabola to the loss function and locate its minimum. This approximation is only really useful if the parabola has positive curvature. Several cases depending on the values of the function and the signs of its derivatives must be considered. When the parabolic approximation is not useful or convenient, we examine the values of the function and the signs of its derivatives to determine whether the learning rate needs to be increased or decreased.
Wait a minute!
In real-life systems, there's a high chance of instability, especially when the network performs some kind of recursion. Calculating the loss function at the current parameters and at the parameters obtained with a tentative learning rate helps us to detect and to avoid instability. We define 3 learning rates. The tentative learning rate that we try at iteration I. The learning rate that we actually apply at iteration I. And the update learning rate that will be used to calculate the next tentative one. To avoid instability, we must avoid extrapolation. If we are unsure of what is coming next, it is best to leave it as it is. The first case that requires special treatment is number 5, which occurs when we find that the learning rate is too low. This is the case when the loss function improves and the slope is negative at both points. We can therefore reasonably expect that a higher learning rate would have been beneficial. If we use a learning rate that is too low, the algorithm will take many steps to approach the minimum of the function. The algorithm will certainly reach the minimum, but perhaps at a rate that is too slow to be practical. In this situation, we update the parameters of the system using the tentative learning rate, because it is expected to be the best one in the range of interest. For the next iteration, we assume that a better learning rate would have been given by the current tentative one multiplied by a factor greater than 1, but less than 2, we have plenty of time to find the optimal one. This updated learning rate takes into account the derivatives of the loss function. Thus, if the function is close to a minimum at the tentative learning rate, the increase will be less than if the minimum appears to be further away. Note, however, that we do not use this update learning rate directly in the next iteration, but use it to obtain the next tentative one by applying an exponential moving average. On the other hand, Case 6 represents the situation where the function does not improve and both slopes are positive. We can be pretty sure that the learning rates used in the last iterations were too high. Although this situation is impossible when using true gradient descent, it can occur when, as is usually the case, a momentum is used to update the parameters of the system. In fact, the optimal learning rate would be negative in order to invert the momentum introduced by the exponential averaging of the gradients. It can be seen that if we continue to use this learning rate, the loss function will get worse at each iteration, and the chances are that we will reach the instability to the right of the function. In this situation, we decide not to update the parameters of the system, as this is expected to be the best decision for learning rates in the desired range. For the next iteration, the update learning rate is assumed to be negative, so the exponential moving average causes the sequence of tentative learning rates to decrease. Cases 1 to 4 represent the situation when neither too low nor too high a learning rate is detected, and when a parabola of positive curvature can fit the values of the loss function and at least one of its derivatives at mu equal to 0 or equal to the tentative learning rate. Depending on the values of the loss function and its derivatives, we distinguish four cases, the first two of which are reserved for future work. Case 3 represents the situation where the loss function improves at the current tentative learning rate and has a positive slope there. Case 4 represents the situation where the loss function deteriorates at the current tentative learning rate and has a negative slope at the origin. These four cases are particularly desirable because we can be fairly sure that the function has a minimum in the range of interest, which can be approximated by the minimum of the parabola. We see that the parabola that fits both values of the function and its derivative at a learning rate equal to the tentative one has a minimum reasonably close to the minimum of the function. So, in these cases, we take the minimum of the parabola as an estimate of the minimum of the function and use this value to update the parameters of the system and provide the updating learning rate. Our main hypothesis is that the optimal learning rate does not vary much from iteration to iteration. We use this assumption to build a slowly changing sequence of tentative learning rates by exponentially weighted averaging of the update learning rates, mu+. We have tried ACME in several deep learning tasks, both in image recognition using CIFAR 10 and CIFAR 100, and in phone recognition at the frame level using LibreSpeech. In this paper, we present the results obtained on the image recognition of the CIFAR 100 database using a wide ResNet of 40 layers and a width of 10. The system is implemented in Python using PyTorch and is publicly available on GitHub. The hyperparameters are quite typical and similar to those used by the authors of the wide ResNet network. When using standard gradient descent with momentum, SGD, the results are very sensitive to the choice of learning rate. While convergence is quite fast for mu around 1, higher values of mu lead to divergence, and lower values require far too many iterations to achieve good results. Note that while mu equal to 10 produces results similar to mu equal to 1, the behavior is more erratic, and in some cases this choice of learning rate led to divergence. On the other hand, while the results for mu equal to 0.1 may seem similar to those for mu equal to 1, the difference is greater than what the graph shows. The final error rate for mu equals 1 is 17.3%, while it is 21.1% for mu equals 0.1. Some people would kill to have a difference of almost 4% in the error rate on this task. With ACME, the initial learning rate does not seem to have a noticeable effect on the results. In fact, it converges much faster to results similar to the best achieved by SGD. Why do we get such a good result? Well, if we look at the tentative learning rates used along the 200 epochs, we see that they converge to very similar values quite quickly. To get a better picture of what's happening, the graph shows the evolution of the learning rates for the first iteration only. We can see that the different curves tend to have learning rate values between about 1 and 10 even before the first epoch is completed. Curiously or not, these values are similar to those that gave the best results with standard SGD. ACME is not only compatible with SGD. It is also compatible with ADAM, ASAM, and their combination. The plots show the error rate versus the initial learning rate after 200 epochs with SGD, ADAM, ASAM, and ADAM in combination with ASAM. The red lines represent the results obtained with a fixed learning rate, while the blue lines represent the results obtained with ACME. The solid lines represent the results on the test set, while the dashed lines represent the results on the training set. As it's clear from the plots, ACME achieves similar results to the fixed learning rate in all cases for the test set, but it does so for a much wider range of initial learning rate values. It can be affirmed that ACME is immune to this value, at least as long as it is low enough to avoid instabilities in the very first epochs of training. In the training set, ACME converges to an error rate very close to 0. Indeed, this convergence occurs very early in the training process. This is actually a handicap for the algorithm, since deep learning is based on the elimination of errors. If there are no errors left in the training material, there is little remaining to be learnt from it. In summary, we believe that ACME is an interesting alternative to standard SGD because it avoids the tedious task of selecting an appropriate learning rate. Of particular interest is the fact that it can be combined with other more sophisticated algorithms such as ADAM or ASAM. The authors believe that the algorithm merits further research. This work has been supported by the Spanish government and the La Caixa Foundation through various grants and agreements. Special thanks to Roadrunner and Wile E. Coyote from Looney Tunes for their inspiration. Connor from Love Voice for lending us his precious voice. And Ellers McDaniel, also known as Bo Diddley, for the soundtrack. Very special thanks to Professor Jose Bernardo Marinho Acebal, also known as Pepe or JB, without whom none of this work would have been possible. Thank you for your attention.